Now students, now we'll be discussing few important things about damped vibration which you get in your exams, and conceptually also you need to know it, because while you design an oscillator, because you are from electronic stream, you will be learning different types of oscillators. In future you might be designing in your project also oscillators, and all of them will be damped, because that is you will never have a free vibrating oscillator, isn't it? So ideal, actually, for a damped oscillator, when you design it, certain factors you have to keep in your mind: how quickly the oscillation dies out. Okay, what is the time within which the oscillation dies within a certain frequency, within a certain value? How, what is the time within which the amplitude of oscillation dies within a certain value? Okay, so what is the energy, how quickly the energy gets damped to a certain specific value? So that defines three important parameters which you need to see while you study damped oscillation. One is logarithmic decrement. Number two is, well, relaxation time. Number three is the quality factor. So these three things you, as a designer, you should have at the tip of your finger when you try to sell it out to your customers, so that to define how efficient your system is, to make people understand the fineness of your design. Okay, so let us look into one by one what each of them are. What is log decrement, what is relaxation time, and what is quality factor? Okay, so starting off with logarithmic decrement. Okay, so you see, the look at the amplitude of damped vibration. It is given by A0 e to the power minus kt, isn't it? This is the amplitude of damped oscillation. What is your k over here? Your k is equal to r by twice m. What is r? R is the damping constant, and m is the mass of the oscillator, isn't it? So let us consider the oscillator to start from a mean position. Okay, so that after a time, say t equal to, because if you consider a simple pendulum, if it starts from the mean position, the total time capital T is divided into 4 parts. So let, after a time t equal to t by 4, where t, capital T, is the time period. Okay, capital T is the time period. Okay, the oscillating particle goes into extreme position. Capital T is the time period. So after a time t equal to t by 4, after this time, what happens? The oscillatory particle goes to extreme position, isn't it? It goes to extreme position. The oscillatory particle goes to extreme position. All right. So let the first amplitude be denoted by A1. Be A1. Let the first amplitude be A1. Then what can you say? Well, then, because it occurs at a time t by 4, then A1 is equal to A0 e to the power minus k t by 4. Agreed? All of you? So then the particle will come to the mean position and go to the extreme position on the other side. So first, after a time t by 4, this is the amplitude, and then the particle will come to the mean position and then it will go to the extreme position on the other side. Again come back to the mean position and go to the extreme position on the same side after a time t. So after a time t, after a time t plus t by 4. Okay, what do we get? Okay, we get the second amplitude. So let that be equal to A2. Let the second amplitude be equal to A2. Okay, so A2 is equal to A0 e to the power minus k t plus t by 4. Okay, all right. Similarly, A3 will be equal to what? How much? A0 e to the power minus k 2t plus t by 4. Okay, like that, if you go to, so it will go on like this. Okay, and then you come to an is equal to A0 e to the power minus k, okay, n minus 1 t plus t by 4. This is what you will be getting. So if you take the natural log, okay, suppose you take the natural log, then taking log to the base e, taking log to the base e, okay, what do we get? We have log ln, okay, a1 by a2 is equal to ln a2 by a3 equal to ln a n minus 1 by a n, isn't it? And this, if you do it, you will see this is equal to e to the power, this is equal to kt. Actually, if you take just the ratios first, a1 by a2, you will see it's equal to a2 by a3 equal to an minus 1 by an, that is equal to e to the power kt. So when you take ln, okay, that will be just be equal to kt, and you call this as equal to lambda. This is defined as the logarithmic ratio between two successive amplitudes. The logarithmic ratio of two successive amplitudes. Two successive amplitudes. Okay, so what do you call it? You call this the logarithmic decrement. Okay, and this is very important. All right, this is very important to obtain, to find the damping, to find to what extent your system is getting damped in a damped oscillator. How quickly the amplitude is falling and to what extent the system is getting damped in a damped oscillator. What is the physical significance? The logarithmic decrement of a damped oscillatory system gives a measure of the rate at which the amplitude of vibration decays. It is given by lambda. So basically lambda is equal to R. So actually lambda is equal to R by 2m into the capital T, which is the time period of oscillation. Okay. Alright. So let's stop over here for log decrement.